Okay, we're back for the second part of your history notes. Of your atom notes. You've already done the history part, and you should have already done the atom poggle activity with a group yesterday. So that's where you should be at. So if we go on, we're going to go through it fairly quickly because this is stuff you probably already did. You should already know from the atom poggle. So we're going to go through fairly quickly just so you kind of see it. So if we talk about this, we're going to talk about the subatomic particles. The first one we're going to talk about is the proton. And if you think about where it would be, hopefully you know from yesterday, it would be in the actual nucleus. It does have a relative charge of +1, so when we talk about a proton, instead of saying how many coulombs it has, we just say it's +1 to make it a little easier for us. And it does have an actual mass of 1.673 times 10 to the negative 24th grams. But if we just say a relative mass, we say about 1 AMU to make things a little easier for us. So protons are in the nucleus. That's where they hang out. They're always there. They're going to be positive. That's why we have little P plus up here. And they have an actual mass and a relative charge. If we go to the next guy, next guy is going to be our neutron. And he is in the nucleus as well. He has no charge, so he is kind of like just by himself. That's why he gets the little zero up here. He also has a relative mass of 1 AMU. He is a little higher than the actual proton, and if you look at his actual mass, he is actually a little higher than that. I have the Homer Simpson picture up here because he's kind of like Homer Simpson. He's really heavy. He's the heaviest subatomic particle, and he has no charge. He doesn't really do anything. So that's where the Homer Simpson comes from, if you were wondering. All right, next guy is our good old electrons, and you should know they're outside the nucleus. They're a -1, so we call them E negative. And basically, they do have a mass, but it's so small that we say rounded, it's 0 AMU. So basically, electrons have a mass. Don't get me wrong, they have a mass, but for our purposes, we're going to say that they're 0. And again, they do have 9.109 times 10 to the negative 28 grams per electron. So you should already know that from yesterday. And then going on even further, what you should have is, when we first talk about the atomic number, remember everything has its own atomic number, and that is its number of protons. So if you look up number 5 on the periodic table and he's boron, that means that boron has 5 protons. If he doesn't have 5 protons, he's not boron. If you look up number 47, that's silver, that means he has 47 protons. If he doesn't have 47 protons, he's not silver. Then we talk about the mass number. The mass number is different than the average atomic mass. The mass number is for one atom, so you may want to write that down. Oops. The mass number is for one atom. We're going to talk about the average atomic mass shortly, but that's for every single atom in the universe. But when we look at the mass number, it's how many protons you have plus how many neutrons you have. Because remember, they're the heavy things. They're the things that actually matter. So that's what we worry about for mass number. And the protons and the neutrons are called nucleons because they're in the nucleus. So nucleons are the things in the nucleus. And then, if we want to talk about being neutral, if you're going to be neutral, and we have things that are charged, so we have our protons that are positive and our electrons that are negative, if they're going to be neutral, then you have to have the same number of protons as electrons. So, for example, if we look up sodium on the periodic table, he's number 11. His atomic number is number 11. That means he has 11 protons. If he's neutral, that also means he has to have 11 electrons. So just keep that in mind if they're neutral. And then yesterday, you guys kind of finished it off. If you're an ion, you're going to be a charged particle. And what that means is your number of protons, and I need to fix this, is not going to equal your number of electrons. So your number of protons is not going to equal your number of electrons. Just be careful. You can't change your number of protons. Remember, if you change your number of protons, You're actually changing your element. So just keep that in mind. So if we look at this, if you're going to be positive, that means you're going to be called a cation, and they call it a cation because you are going to be attracted to the cathode, which is kind of weird. But if you are going to be positive, that means you're going to lose electrons. You can't gain protons because then you're going to change what you are, but you can lose electrons. And then if you're a negative ion, you're going to be called an anion, and you're going to gain electrons. But notice, it's all about the electrons. If you have 17 protons to begin with, you can only have 17 protons. You can have more or less electrons, but you can't have more or less protons. And if we look down here, it's right here, both these atoms have 3 electrons at the bottom of the screen here. And we look, this one guy is giving the other guy an electron. So this guy got an extra electron, so now he's negative. And the bottom guy lost an electron, he only has 2 electrons, so now he is positive. So again, keep in mind it has to do with electrons, not the protons. All right, then you also talked about isotopes yesterday. And isotopes are going to be atoms of the same element. And if they're the same element, that means they have, if you remember, same protons. But they're going to have a different mass and basically a different number of neutrons in them. A lot of people think isotopes are weird. If you watch The Simpsons, they have like the Springfield isotopes. Every single element on the entire periodic table has isotopes, and most of them are not harmful to you. Most of them are just completely natural. There are some isotopes that are not naturally occurring, and there are some isotopes that are dangerous. But just because you are an isotope does not mean you're dangerous. And there's lots of isotopes that don't emit radiation at all, which means they don't give off any kind of bad energy coming at you. So you just have to be careful with that. And then over here, we're saying a nuclide. Nuclide, this would be, I would underline that is a vocab word. It's in a specific isotope. So it would be like carbon-14 versus carbon-12. Carbon-14 would be a specific nuclide, and carbon-12 would be a specific nuclide. They're both carbon, but different way. And then if you look at the picture at the bottom here on the slide, it's just showing you that hydrogen does have different isotopes. So the hydrogen 1 is the one you're used to, but there is also this hydrogen 2, which is called deuterium, and there's actually even a hydrogen 3, which is called tritium. And then kind of just a cool look here, if you look on the left, you have this cup with ice in it. That's normal ice, which is the normal hydrogen, the hydrogen 1. Hydrogen 1 is much more common than the other ones. But then if you look on the right, that's heavy ice, which is made with deuterium. It's not dangerous, it's not going to hurt you, but it actually does sink in water because it's heavy as opposed to the normal one. So being a different isotope can kind of change how you're going to act with some things. All right, and then if you go to your, last thing we're going to do is the isotopic symbol and isotopic name before we take a little break. So if we look up here, when you look at this, again, you should have this, but if you look at this, the guy on top is going to be your mass number. The bottom down here is going to be your atomic number. And if you have one, your charge is going to be on your upper right. If you don't have a charge, you don't write one. You don't have to write it 0 or anything. So again, isotopic symbol, you're going to have this mass number, you're going to have your atomic number, you're going to have the symbol, like the actual chemical symbol, and you may have a charge if you have one. So if we look up this potassium on the left, it says that our atomic number is 19. Our atomic number tells us our protons, so we have 19 protons. This guy has no charge, which means that our protons and electrons have to equal each other. So we have 19 electrons. And then the last thing we want to get is our neutrons. And you want to remember, up here, this is our mass. And the mass is our protons plus our neutrons. So if our mass is 39, and we have 19 protons, that means we have to have 20 neutrons. And all I did was take 39 minus that 19. If we look at our calcium over here, its atomic number is 20, which means we have 20 protons. It does have a charge, so we do have to worry about that. It's a +2 charge, which means it lost 2 electrons. So instead of having 20 electrons, he only has 18. And then again, our neutrons, his mass is 40. We have 20 protons, and that means we have to have, oops, I don't know why I didn't write that, 20 neutrons. Let's try that again. So you should be able to do those. You're going to be doing lots of these for practice tonight. It should not be hard. It should be simple. You should have to remember the rules. And then the last thing we're going to just talk about quick is the isotopic name. So up here we had our symbol, which is the real short way, but now we can look at the names. And this is just saying, okay, if I have a specific type of element, isotope, how do we write that? And you're just going to write your element name and then what is its mass. So again, if you've heard of carbon-14 and carbon-12, that's an example of it. So down here we have chlorine, that's the element, and its mass is 37. And you could also have uranium-235 and uranium-238. And that has to do with what's going on in nuclear reactors.